Good afternoon, and thank you for joining us in a terrific occasion for the Department of Chemistry, the College of Natural Science at Michigan State University. I'm Rob Maleshka, the chair of the Department of Chemistry. I want to welcome everybody to the investiture of Professor Tom Hammond as our James L. Dye Endowed Chair in Materials Chemistry. The program today will touch briefly on the importance of endowed chairs, the importance of those chairs to the department, to the college, to the university, their long-term impact, and on faculty positions and that will have a continued excellence in the university environment. Most importantly, of course, we're going to hear from the honoree, Tom Hammond, the recipient of this prestigious chair. We will then have the investiture, and of course, it wouldn't be complete without some closing remarks from Professor James Dye himself. With this investiture, Tom, as the Dye Chair, he will change the Department of Chemistry for a long time. As you will hear from Paul Hunt, the Senior Associate Vice President for Research and Graduate Studies, and more importantly, a professor in the Department of Chemistry, the establishment of chairs like this is a significant step forward for us. And it is one that will endure for generations to come. I will now turn the podium over to Senior Associate Vice President for Research and Graduate Studies at Michigan State University, Professor of Chemistry, Paul Hunt.
Well, good afternoon. Thank you, Rob. This is obviously a joyous day for all of us. I was thinking that whenever one talks about an endowed chair, one wants to think long-term. And since this is the sesquicentennial of the American Civil War, which gave rise to the Morrill Act, which gave rise to Michigan State University and other similar land-grant institutions, I would use a Civil War story as a metaphor for the immense contributions that Professor Jim Dye has made to Michigan State University. The story is that when the Civil War broke out, Abraham Lincoln got in a carriage and went over to the War Department to meet with the commanding general of the U.S. Army at the time, who was a guy named Winfield Scott. And he had served a long time, and Lincoln entered the office, and on the left was a picture of General Scott taking Fort George and freeing the Niagara River and the Great Lakes. And then Lincoln turned around and looked to his right, and he saw General Scott in the Mexican War scaling the heights outside of Mexico City and being victorious. And then he turned to the center, and at the desk sat General Winfield Scott. This is sort of like going into the east end of the chemistry building basement where physical chemistry lives. The issue for us is we don't have portraiture of immense contributions the way the War Department did at the beginning of the Civil War, but I wanted to share with you first off a couple of examples of what might be on those portraits if we did. And since I had the privilege of looking at the dean's remarks and the chairperson's remarks a few minutes before the meeting, I'm going to use examples that aren't in theirs so I don't step on their speeches so you guys can relax. Something that some of the folks in the room are well aware of and may have participated in is that Professor Dye was a really first-rate kineticist early in his career. But more than that, he has an excellent claim on being Michigan State University's first computational chemist. And something that a few of us in the room know is that KinFit, which was a highly sophisticated kinetics analysis program that the Dye Group produced, was for decades the single most requested by external users piece of software emanating from Michigan State University. It had many fine features, but for those of us who know something about computing, one of its most impressive aspects was that it was written before the era of virtual memory, which meant that the whole code fit in about 64,000 words of memory, which is amazing to people who use memory like it's water today with virtual machines. So our hypothetical new university president, looking to the left on the hallway, sees the computational chemistry victories of the Dye group. And looking on the right, more recently, Jim was a pioneer of some of the most advanced techniques for doing materials science research. He's the first person from whom I heard the word squid in a context that was not marine. And, if you're not familiar with squids, there are lots of chemists in the room. Just ask one and they'll tell you about why that was impressive. But beyond that, he was, and continues to be, an outstanding citizen of the university. And I wanted to make points that also, I think, make the Dye chair a reminder to all of us as time goes on of the importance not only of first-rate science, but first-rate scholarly citizenship. Once upon a time, when Gordon Geyer was acting president, MSU found itself in a situation where there was a really nasty intellectual integrity issue, and Gordon Geyer decided to pull together a blue ribbon committee to talk about what to do about that in particular and intellectual integrity in the university in general. And he turned to Jim to chair that committee, and the result was what is still known in the administration as the Dye Report. And that was a role of citizenship that was one of many, including answering the university's call to direct the Center for Fundamental Materials Research for a term of years, to be chairperson of the Department of Chemistry for a term of years, to be acting dean of the College of Natural Science, all while maintaining a research program that eventuated in his election to the National Academy. So when one looks at backward and sees this kind of trajectory, the institutional trajectory that it represents and the personal trajectory of Jim and his group, and then one looks forward to the innovation that this particular chair represents in terms of materials chemistry, innovation which Jim has guided significantly with his input, one sees precisely the things that we would hope the university would find with increasing regularity, the commitment of generous donors, a truly worthy honoree, and as we will hear later in the session today, an inaugural holder of the chair who gives every promise of maintaining the trajectory of excellence in the department. Please accept my thanks and that of the President and the Provost for your presence today, and best wishes to all.
Well, for those of you who don't know me, I'm Jim Kirkpatrick, Dean of the College of Natural Science, and it is my distinct pleasure to welcome you all here on behalf of the college. We're really glad you could be with us today. I think this is the biggest group we've ever had for an investiture, so it's a kind of commentary on both Jim and Tom, and I appreciate you all being here. So, most importantly, Tom, on behalf of the college, congratulations. We're really pleased that we were able to do this, and this is very, very well deserved. I'm looking forward to your talk. As Paul said, this is also an opportunity to recognize and honor Jim, and we'll be hearing from Jim later in the program. So Paul talked a little bit about Jim's history, but for those of you who weren't at Jim's presentation yesterday afternoon, where he blew some stuff up in classic professor style, talk a little bit about him. So he's been at Michigan State for more than 6 decades. Certainly, as Paul said, one of the most successful and influential faculty members that this university has ever had. He's most well known, at least to me, for his work with alkaline metals that earned him the recognition of his discoverer of of a really quite novel and important class of compounds that we call alkalides and electrides. And as Paul said, he was elected to the U.S. National Academy of Sciences for those accomplishments. Now, Jim retired, and my notes here have that retired quote, from the university in 1994. That was, if I can do arithmetic, 20 years ago. So, 20 years as emeritus faculty member, but he's continued deep engagement with the university through his research and mentoring of students. So, Jim, again, on behalf of the college, thank you for all you've done and you continue to do, and this is certainly, it's most fitting that this chair is named in your honor. Also want to opportunity to express our thanks to Larry Dalton, who's the donor who was instrumental in making this endowed chair possible. Larry is unable to be here today, but he was a student of Jim's in the mid-1960s and has maintained a lifelong connection with him. And Larry feels strongly that Jim should have received the Nobel Prize for his work. He's told me that. So you know, that's the level of contribution that Jim's made. Again, as Paul and Rob have said, endowed faculty positions are absolutely critical to the future of the university. They are the hallmark of really every great university and absolutely critical for Michigan State's competitiveness nationally and internationally. They're permanent, and this permanence assures that we have outstanding teaching, research, and leadership in perpetuity. So, like individuals, universities are subject to the vagaries of the short-term economy. But our work has to endure and continue through good times and bad. Our time horizon, if you think about it, universities, Paul kind of alluded to this, our time horizon is decades and centuries, right? And we have to be able to think on those time scales, and endowments provide us the opportunity to do that, to provide a consistent and permanent source of income that can provide flexibility to move resources around where they're going to have the greatest impact, really wherever the need arises. So again, to repeat what people have said, the Dye Endowed Chair in Materials Chemistry will play a very significant role in guaranteeing the continued capacity of Michigan State to be a national leader in materials chemistry and ensure that the future alumni have the education they need to be leaders in chemistry or in whatever direction their life takes them. So, Tom, again, congratulations. Well deserved honor, and we're looking forward to great things.
Thanks, Jim. And thanks again for everybody for being here today. This really is, again, a very exciting and important occasion for the Department of Chemistry. As chair, I've had the honor of presiding over the investiture now of 3 endowed chairs. But this, the James L. Dye Endowed Chair in Materials Chemistry, is the first endowed chair that truly resides in the chemistry department. And it's one, therefore, that will have, again, a lasting impact on the department for many years. It is, again, an honor to be able to award this first endowed chair in the Department of Chemistry to Tom Henry. Tom is a tremendously creative chemist. He's an internationally recognized expert in the area of solar energy conversion, where his work represents a unique confluence of material synthesis and design, fabrication and characterization of nanostructured devices and theoretical models. As you've heard throughout the program, having the ability to offer these endowed chairs enables departments to hire outstanding faculty. And in fact, the previous 2 investitures that I presided over, we were able to bring Melanie Cooper, Professor Melanie Cooper, and Professor Kenny Merz, from other universities to our department. But in this case, we're able to think about using this endowed professorship to retain a top-notch faculty member. This is one way for us to keep ahead of the competition, if you will, and follow in the footsteps of Jim. I expect Tom to be here 61 years. Per Larry Dalton's request, up Jim just a little bit and win us our first Nobel Prize. That's too much. But the other part of this whole endowment equation is that success breeds success. Donors really don't want to wait to see their generosity at work. And thus awarding this chair to Tom, a well-recognized scholar, is a way to prime the pump for future endowments in the department, in the college, and in the university. And speaking of donors, I think it is important for me to add a few more words to Dean Kirkpatrick's comments on Larry Dalton, whose generous gift was really integral to the establishment of this important chair. Larry graduated in 1965 from the MSU Honors College with a BS in Chemistry and Mathematics. It was during his sophomore year at MSU that he was working on a dual degree, and became involved in undergraduate research with Professor Dye. Larry then began his master's degree his junior year, studying with Jim, and he graduated in 1966. In Larry's words, Jim Dye changed our ideas of chemistry. He taught me how to approach difficult problems. I learned not to be afraid of any topic. Dye was an excellent teacher, as he would lead you through an understanding of the most difficult problems. Larry then went on to earn his PhD from Harvard in 1971 and has embarked on a very successful independent career. Larry is best known for his work in polymeric nonlinear electro-optics. He is currently He's currently at the University of Washington, where he holds the George B. Kaufman Professor of Chemistry and Electrical Engineering. Again, the department is really deeply grateful to Larry for his generosity in establishing this important chair. And as well, we are deeply grateful for all of those in the audience who added to Larry's priming of the pump, if you will, and really made this endowed chair possible. Again, another key aspect of these positions is that departments with the best faculty, they attract the best students. And it's the best students who, let's face it, make the best faculty. So by having this endowed chair in the department with Tom at its helm, if you will, it's an ability for us to turn that pump, if you will, and really make the department the best that it can be. In initiating and propagating this cycle, it takes significant resources. As Dean Kirkpatrick mentioned, these endowed positions are a way in today's financially constrained environment to secure these resources in order to attract and retain this caliber of faculty. Now, before I turn the floor over to Tom, I'd like to give you a quick overview of his path to MSU. Tom is originally from Alaska, so he came south to MSU. He earned his undergraduate degree in chemistry from the University of Texas at Austin, his master's in chemistry from the University of Massachusetts, Boston, and then his PhD in chemistry from the California Institute of Technology in Pasadena. Prior to joining MSU in 2009, Hammond spent 2 years as a postdoctoral fellow at Northwestern University. He is the recipient of numerous awards, including very recently the Royce W. Murray Young Investigator Award. He's a Camille Dreyfus Teacher Scholar. He's received the Alfred P. Sloan Research Fellowship. He has an NSF Career Award and a DOE Department of Energy Early Career Research Program Award. As an associate professor and the inaugural James L. Dye Chair in Materials Chemistry, Tom will continue to advance the frontiers of inorganic materials and photoelectrochemical energy conversion science. With that as the backdrop, I think it's time to hear from the guest of honor, Tom, about some of the exciting work that he's been doing in the area of materials chemistry. Tom?
Thanks, Rob. So I came in 2008. But I guess I was in the lab. Maybe you didn't notice in 2008 because I was in the lab pretty much all the time that year. So Maybe it didn't seem like I appeared till 2009. So that means I've been here 6 years, so I'm only an order of magnitude away from catching up with Jim Dye. So I look forward to trying to match that, but I don't have that high of hopes. So I guess I first want to tell you about what motivates my research interests. I'll talk about some of the research that my group is working on and has been working on over the last 6 years. But I really have to say a lot of what we're working on are things, at least concepts of what I started when I was applying to graduate school. And I knew when I got to graduate school it was going to be a lot of hard work, and I was ready to work hard, but I really wanted to work hard on something that I thought was a really important topic. And so then I started to think about what are the really important problems in the world. And well, this is a recent report, but this is when I started to think about alternative energy, research in alternative energy, because it was already known, I don't know how long that was, 15 years ago when I was applying to graduate school, now that the world's population was growing and the populated parts of the world are industrializing, and that's good, and this is causing a huge increase in the demand for energy, and that's going to increase. And then you worry about what are the consequences of this. I mean, certainly I want the world to develop and industrialize, and this is going to require a lot of energy. And so then where does that energy come from? And it comes from fossil fuels, and then it's a concern about what happens, what are the environmental consequences of continued burning fossil fuels. So that's really what I thought was the big problem, and every other problem of supplying the world with food and water and education. These are all linked in health, and these are all linked with energy, right? You can't have increases in technology without increasing our supply of energy. So and this is personal. I'm actually not worried about the environmental consequences for me in my life. I think we're going to be fine, but it becomes personal now when I think about the world that my son, he's only 2 now, but he's already a Spartan fan, as you can see. That's his favorite shirt. So I just think about the world that he's gonna live in now. So this is something that I still think about. It still motivates me, and I still think energy is the most important problem for scientists to work on. And at least that's what I'm going to work on. So if we don't continue down the path of burning fossil fuels, then you have to think, well, what else are we going to do? Where do we get our energy from? And really, there's only one answer that makes sense, and that's solar energy. And that's really just because of the abundance. There's more solar energy, more energy from sunlight hitting the Earth than all other resources combined. It far outweighs all fossil fuels and wind and nuclear power that's available. Maybe not nuclear, but that's another day, another topic. Okay. So then we actually know how to harvest solar energy pretty efficiently already. This has been around for decades. And the problem is really one of cost. My wife tells me that we can't afford to put solar panels on our roof, and I believe her. And that means if we can't afford it, then I can't expect people in India and China and Africa to try to buy solar panels rather than burn coal, which is just what makes sense, right? So we have to make that answer very easy for them and sort of resolve the problem of can we provide cheap solar energy that's also efficient and scalable. So it has to be scalable to meet the world's demands, not just our demands. And then that becomes a really hard problem. And so one of the systems that we're interested in is a dye-sensitized solar cell. And the reason is because its substrate is, well, they're very easy to make. It's essentially white paint, and it's hard to beat in terms of cost effectiveness, just white paint, painting on a piece of glass. You heat it up and you soak it in dye and squish it together with another piece of glass and you have a solar cell. And that's what they look like when we make them in our lab. And well, they're starting to come into the marketplace. These are dye-sensitized solar cells, so you can soak them in different dyes, make them different colors, so they look quite nice. But they're not that efficient. And so therefore, this is the science problem that we want to work on. What limits the efficiency? What understanding gaps are there that we can address and then allow us to sort of design the next generation of solar cell that's going to be cheap and efficient and scalable and all these requirements that are really necessary if you're going to make a dent in the world's energy picture. So this really becomes a materials problem then. So this is sort of a schematic. It's a little bit complicated. I'm not going to walk you through that. But I will tell you about a couple of the things that we have found in the last couple of years. And that is shown here in the yellow. I don't have a laser pointer. These are electrons. We've been able to sort of separate, as a consequence of having this as a cheap material, that it's white paint, you have a lot of defects. It's not like the really pristine silicon solar cells that you currently can buy. And these defects are in trap states. And this can be a problem. So we've been able to characterize the fraction of electrons that are in trap states versus the ones that are free and mobile in the conduction band. We've been able to separate the behavior because they actually have very distinct behaviors in recombination. So in general, in a solar cell, you want to absorb light, and you create electrons in holes. And then you have to move them, separate them, and collect them at different electrodes, and that makes a solar power, right? And so then you're always fighting against those charges coming back and recombining. That's general for every solar energy conversion system. And so in this case, the recombination mechanism is interfacial electron transfer. And so that's what we spent the bulk of our time trying to understand the details of that, how electrons go back from the white paint or these nanoparticle TiO2 materials, and they go back into solution. Okay. And we've also struggled, and I think we've been recently successful with trying to solve what seems like it should have been a solvable problem, but it hasn't been solved for the last 20 years, is trying to understand where the energetics map out the energy of a conduction band in a nanoscopic material. And there really was no method to do that. So one of the things we've gotten interested in, just because we have to map out the energetics if we want to understand, get a good physical picture of how things work. So we've developed a methodology to monitor the absorption of free electrons and separate that out from trapped electrons and monitor that as a function of temperature, applied potential, and correlate that with a decrease in absorption here. And this has allowed us to quantify the actual absolute conduction band energy for the first time, I think. Okay. And so now this is starting to give us some design rules and saying we understand, I think, in a lot of detail of how a dye-sensitized solar cell works. We understand the limitations. We have a good picture. And so now we're using this to start to develop sort of the next generation of dye-sensitized solar cell. And I think that's where we're headed over the next 5 to 10 years, hopefully 5, actually. But we'll see. So there's another big problem with solar energy conversion, and that a lot of you have probably noticed that at night the sun goes down, and then that tends to be a problem because then you can't power things if you're relying on sunlight. So we have to find a way to store solar energy. And as Rob pointed out, I grew up in Alaska, and then the sun goes down for half the year. And, well, we don't want to live without electricity for half a year. And so we've been working on ways to store that in chemical bonds. So this is a prototypical example of using sunlight and trying to concentrate it and store it in chemical bonds. So driving chemical reactions with solar energy. And this is a prototypical example of splitting water. And then you evolve oxygen and hydrogen. And now you can use hydrogen if you were able to store that, use it in a hydrogen fuel cell, for example. And so now you really just need sun and water. And if you can do this conversion efficiently, you're set to go, basically. Okay. So this is sort of a diagram. We've been looking at iron oxide as our model system. And you absorb light, right? We make an excited electron in a hole. And then we need to separate those. But there are lots of mechanisms that are fighting against being able to separate and collect these charges. And those are shown here in red. And then once you get charges to the interface, you have to collect those and do the right chemical reaction versus recombining or doing some other reaction that you're not interested in. And so these are all, we've systematically gone through one by one. How does the back interface, how does that control the ability to separate charges and collect them? How do the bulk properties affect it? How the surface, which turns out to be the most important thing, is the water oxidation reaction on the electrode surface. How do all of these ultimately affect our ability to efficiently take sunlight and split water with that? So we've kind of gone through systematically step by step and looked at each of these reactions and tried to find what is the rate limiting step, and then using that to devise strategies to sort of overcome that through material synthesis strategies, addition of catalyst. And so this is actually, I can show now quantitatively our progress. This is one of representative in the red curve of one of the first JV curves we took in my second year. So a current voltage curve is a measure of the efficiency of the system. So the larger current at a certain voltage, so the more the curve is that way, the higher the efficiency. And now we've systematically marched from this red curve, which looks terrible if you ever look at if you're ever familiar with photovoltaics, up to the purple curve, which is now, I think now we're the best in the world at making hematite photoelectrochemical cells. And that's really been a sort of a long systematic march towards improvement. So we still have a long ways to go, but I like the methodology that we've developed, and I'm still excited about seeing how far we can push this. So a third topic we work on in my group, and this is really inspired by my colleague Mitch Smith, which it took me a couple of years probably to really catch on and get excited about it, but now it's something I'm very excited about, and that is in the chemistry of ammonia. So that actually starts to bring us back to some of Jim Dye's early work on looking at liquid ammonia. So now we started to work in liquid ammonia, and the idea is, well, there are two reasons why you want to look at ammonia. One is hydrogen. If we are successful at using sunlight to split water and you're making hydrogen gas is not that easy to store. It's not that easy to transport around the country, but ammonia is. So if we can take sun and air and water, and with the right catalyst, you can convert that to ammonia. And now not only do you have a way to store solar energy, you also have a way to make fertilizer. Right? So this is a way to use renewable energy sources like wind or sun power, make ammonia on site, and use that to fertilize and increase the ability to farm around the world. Okay. Of course, if we were successful in this, now we have to find a way to get the energy of ammonia back out. So we have to, there are two ways to do that really, is to do a direct conversion of ammonia to energy, or we can split that back, get the hydrogen back out, and use that to power a fuel cell car. And Toyota has recently, this year, they're rolling out with commercial hydrogen fuel cell vehicles. So I think that this actually has a chance of catching on in the future, whether it's hydrogen or whether it's ammonia. I'm not sure. That's, I guess, our challenge to try to solve these problems. So this is our first example of doing electrolysis of liquid ammonia. We have a long way to go, but I think this is the second example. There's one example in the literature. We're slightly better than them. I think we've sort of worked out what the actual reactions are happening at the electrodes, and now this is giving us hopefully the insight to develop new catalysts. And I think this is the direction that my research is going to go in the future, is really all the action happens at the electrode interface, so it's heterogeneous catalysis, and looking at chemical reactions at electrode surfaces that is going to be a big part of my research over the next, well, decade. It's hard to see further out than a couple of years, but let's say decades. Okay. So those are the three main areas, all under the guise of solar energy conversion in some aspect. And of course, I'd like to thank, well, first my colleagues up there. It's the colleagues and the people at Michigan State who make it a lot of fun and also really exciting to work there. And these are my first two students who were brave enough to join my group when I came to Michigan State. They got here the same time I did. Ben and Jesse. Ben is not a very good sailor, but a very good chemist, which turns out to be more important. And of course, not only my colleagues, but my students, not the first two students, but this is a recent picture of my group and all the students and postdocs who've done the work that I've showed you. And of course, Laura for agreeing to marry me and move to Michigan, and our son, Max, who provides daily inspiration. And that, he's still wearing his Spartan shirt, notice, and that's not on the same day, or planned. That's just how it comes out. And yeah, thank you for this honor and your attention.
Now is the time for the formal investiture, which will be carried out by Professor Hunt.
Before I do the investiture, I'll sort of show off what you can hang on the wall. behalf of the Board of Trustees, President Luann Simon, Provost June Hewitt, and the rest of the administration and faculty of Michigan State University, it gives me great pleasure to invest you as the inaugural James L. Dye Professor of Materials Chemistry.
I will now turn the podium over to James L. Dye.
I just about exhausted myself yesterday trying to compress the research of 61 years into 60 minutes of talk. And as someone pointed out, that means only one item per minute if we want to do it that way. Well, it's a great honor and privilege that you were able to provide the funds, someone, Larry Dalton in particular and others as well, to endow this chair with my name for Tom Hammond. Tom is a great researcher, great teacher, great chemist, and I'm sure that much of his research in the future will help us to understand the nature of solar energy and the nature of materials chemistry in general. I noticed that his major effort that he started today was on dye-sensitive research. That gives a double meaning to this. In addition to being an excellent researcher, he's also a super chef and wine connoisseur, as Angie and I found out last month when he and his wife invited us over for a dinner with some other people, and we had a great time, and you did a great job. I really appreciate that. I look forward to following his research. I've tried to follow a little bit of it in the last few months, but I still don't know very much about it. The more I can learn, the better off, and I'm sure I'll get information from Tom about what he's doing in the future, which is really great. Now, I'm grateful to many alumni and friends, especially my good buddy and friend Larry Dalton, who has contributed a basic challenge that has been met by a number of you and others, alumni and friends throughout the country. Larry and I go back a long ways. He got a master's degree under my direction, but he did most of his work as an undergraduate and dual master's candidate, and it certainly was a breakthrough type of work he did here, which has been followed up by much good research since that time. He's also a great fishing companion. I've gone on 4 trips to Brazil, one with my wife who caught the biggest fish on the trip. In fact, her peacock bass she caught was only 1 pound short of the world record. And so Larry and I have gone together with our son Tom and lots of friends to Canada, usually every year, trying to get some of the record fish that we can get, but more importantly, good friendship. And I'm real happy to acknowledge Larry as a great friend and a great chemist. He really is good. So I'm grateful to everyone who's done that, and the interest in such endowments, the interest and income that it earns goes a long way toward helping out research within chemistry and within the university. It will continue to expand the outstanding research that already is done in the department, and I would just say that additional support is always needed. Chemistry needs as much help as they can get in this day of shrinking budgets and very great difficulty in trying to get outside funding for fundamental research. Such an endowment provides the opportunity to expand and carry out this kind of work, and we certainly want to continue that. Additional support is always wanted. In my 61 years as a faculty member at Michigan State, I've seen tremendous increases. I mentioned some of them yesterday, talking about the difference between what happened in 1953 when I joined chemistry at Michigan State University and what it is now. There's been tremendous growth in the amount of research, the way it's taught, and a bunch of other things. The spirit of cooperation and collaboration is the key to this. In contrast to many other departments, many other universities, there's been great cooperativity and interaction with people in other areas. I don't know how to do most of the stuff we did, but lots of people around do. And so as a result, I have had published joint research papers with 23 MSU faculty and staff, including 12 in chemistry, 7 in physics, and 1 person each in biochemistry, biophysics, and geology. So the spirit of collaboration has just been absolutely great, and we want to continue that. That has helped to make it a great department and a great university, and the more we do this, this was exemplified by our establishment 2 years ago. Paul Hunt mentioned the CFMR, Center for Fundamental Materials Research, which got people talking to each other, doing research together, more in a greater amount than we had done before. Now, when I talk to students about career choices, I always advise them to try to get a position that is so much fun, they do it even if they weren't paid. Okay? Now, certainly that was the case for me. I've been retired for 20 years, but I still go into the lab every day and work with undergraduates. I currently have 4 very talented undergraduates doing research in my group. It's a little hard to get things done in a short time with undergraduates who are busy taking courses and doing other things. But nevertheless, I have great fun in doing that. And besides, Angie says, good thing for getting me out of the house. Now, finally, I want to be sure I got the names right on everybody. Finally, I would like to express thanks to all of those people who made this event possible. A lot of work went into it, I know, and I want to especially thank Karen Wink and Elizabeth Wheeler of the College of Natural Science for the efforts they put in, and Rob Maleska for all the work that was done, not just by him, but by a number of members of the chemistry faculty. And this honor is something I just never expected, but I love it. I want to thank you all for honoring Tom Hammond and me by coming to this event. Thank you.
I'm glad I remembered to bring Jim up. So now, if you would like, next door, the college has generously provided us with an opportunity to have a reception to congratulate Tom in person, to thank Jim for his many years of service to the field of chemistry, and of course to Michigan State University. I look forward to meeting as many of you as I can myself in the reception, which is right next door. Thank you all.
Some advanced French. She's very good at French.
It's my usual awkward talk. I don't even mind.
So, well deserved. Congratulations. Communicating with his
Back and forth.
people that are working on the project.
Our worlds are much smaller now than they can.
Oh,
Yeah, they really.
I've already had a whole bunch of emails watch the program yesterday.
Really?
Oh, yeah.
Oh, good.
Super.
He heard from Mark DeBecker in France.
Okay.
I logged into it this morning and it said there are now 5 people watching this. Today's the morning.
Yeah.
There were 25 of us that went next door because we couldn't fit in the room, and it was live streamed into the auditorium next door.
Congratulations.
I think when I teach,
Walk in on the first day of any semester with a medallion.
yeah, he's, no, he's not that old.
When Jim was on trip?
Yeah, it was probably the last person he hired. Because Blanchard was hired by him. Do you remember that? I don't remember. Everybody's told me they're all great. Now, Jim was the chair when I interviewed in the spring of 1989. Yeah.
And you hired him, right?
Yes, I did. Like you was impossible. I knew nothing about
I told him.
Tom, you need to wear the medal to class on Tuesday. And just don't mention it. Just show up with it on your neck. It'll be great. Oh.